Right, central limit theorem. What does a central limit theorem say? Now, x can be any distribution. X can come from any distribution you want. If you take a sample of values of x and take its mean, x is a random, so x bar, the sample mean, is also random. If n is big enough, roughly 30, again, there's some wiggle room on that, then x bar will have a normal distribution, completely regardless of what the distribution of x is. And this is so powerful. It is such a big result. It is why the normal distribution, roughly, is called the normal distribution. It's why it's everywhere, is because if you start taking samples and averages of stuff, then you will end up with a normal distribution. We don't have time to do it today, but I've done it with students before where I've literally generated numbers from any bunch of distributions and we've tracked it and it does come out as the nice bell curve. So here we got 1, 2, 3, 4, and 6 on a spinner, right? One, 2, 3, 4, and 6. 1/5, 1/5, 1/5, 1/5, 1/5. How do I know it's 1/5? Fair. Is this uniform? It is not uniform. Why? Because that gap there isn't the same as all the other gaps. So it is not uniform. Okay? But we can still find E of x. It's the 16 over 5. I get 3.2. And we can get var of x. E of x squared is 1, 4, 14, 30, 66 over 5, which is 13.2. So var of x is 13.2 minus 3.2 squared. And do you know what? I'm running out of mental maths here. If you think I've made a calculation mistake, do hop in and tell me. Please do. Now, so question from Mudassir, sorry. What is x bar? I will get your name right at some point, right? We're going to spin it 80 times, take the mean of those 80 spins, call that x bar. And it is random. If I did it another 80 times, I'll get a different 80 values. I'll get a different x bar. So x bar itself, which is the mean of 80 spins, is random. But doesn't matter that this is this weird, not quite uniform distribution. Because we've done it 80 times, x bar will follow a normal distribution with a mean of 3.2 and a variance of 2.96 over 80. We're not going to go into huge detail as to why. Again, we're low on time. Okay, but remember, this is the variance. This is variance here. So we want now to find, okay, 3.2. We want to find the bottom 10% of values. We want to find k so that we land in the bottom 0.1. To the calculator machine. Right. Normal distribution. We want the left tail. I don't know. Let's put x is 2 for now. We'll take a guess. Now, sigma here is square root of 2.96 over 80. You can do that directly in your calculator. That's not a problem. Just use brackets. When you're in here, it won't be doing the fractions for you particularly nicely. I've put 2 in as a first guess. It's going to be a terrible guess. Oh, actually, that's fairly big. Actually, because this variance is tiny. So let's change it. We want the area to be 0.1. So that's going to tell me that k is 0 2.95 to 3 sig fig. 2.95. Again, real thing to pay attention to, that is your variance, which is why when I popped it in here, I had to square root it. All right, I had to square root it. That is a source of mistake. So that is our central limit theorem. It tells you about the distribution of these sample means.